I don't think we're watching it.
All right, good afternoon. Welcome. Thank you guys all for coming. So we're going to be doing a really special treat for everyone here. This Cinda, as you know, is leaving us for UBC, but not before she gives one final lecture. So to introduce her, we have the Department Head of Computer Science, Rob Rutenbauer.
Thanks, Wade. It is an honor and a privilege to be able to spend approximately 75 seconds introducing what I've been told resolutely we are not allowed to call the last lecture. The last time somebody in our universe did the last lecture, they very shortly thereafter expired. Yeah, go look, it's famous. We are hoping that Cinda establishes a sort of a more positive association for final lectures by being willing to do this at scale, right, for everybody. It's been a privilege to get to know Cinda over the last 8 or so years that I've been at the University of Illinois. You may know some of her background, you might not. Are you aware of the fact that she has a PhD from the best computer science department on the planet? Now,
I knew you could do it.
Even computer scientists can do that. That's amazing.
We're going to do the wave later.
Oh, cool. Are we going to sing? Yeah. Okay, that's cool. She might have just gone on to become, your standard garden variety computer science, world-dominating nerd. But instead, she decided that she was going to hang around here and teach the best and the brightest, people like you. So she's much more than just a faculty member here. She's literally a force of nature. She's changed the place in the curriculum for the better. She's been the face of some of our most significant outreach efforts to things like women in computing and girls engaged in math and science. She's a colleague, she's a friend. It is an unfortunate truth that really, really good people sometimes find really, really good opportunities that don't keep them in your neighborhood. Sometimes these things involve oceans, right, and strange foreign lands, right? But we're not that far away, right? We hope to be able to see her, occasionally, and I'm sure she'll have an amazing webpage, and we'll be able to follow her progress in the future. And so with that, I'm just going to hand this over to Cinda.
Let's just plug in. I don't care. Yeah. I know how to do this. I've done this part of time too. This isn't even the part making me nervous. Okay. Whoa. Oh, that's fun. We're just going to do that for a while. Okay, and I'm going to adjust. We kind of messed with things earlier. Oh, I don't know. This is not going to work right. Well, it's the background. Hopefully the images will show up, because after all, that's kind of a large part of what this is about. So the title of my talk is Strongly Connected Components. So raise your hand if you have recently taken CS225. Or recently, like yesterday. As most of you well know, we don't just gracefully ease out of the end of the semester. We come crashing into the last semester learning Dijkstra's algorithm in the last half hour of class. And I have always felt like there's about, at least 2 weeks worth of stuff that I still have to tell you. One of the key topics that I never feel like we get to talk about is strongly connected components. This is simply an application of traversal in a graph, and it is really, truly the next thing you need to learn in CS225. Luckily, CS374 picks it right up, and you're not missing it, I'm sure. But I thought, since we just finished class yesterday, I would take advantage of the opportunity to talk about strongly connected components today. There has never been a better talk title, right? There are lots of metaphors for connectivity, and there are even more better metaphors for strong connectivity. One of the most obvious, and it's reinforced by the people in the room, is the connection between people. Now, this talk cannot be about that because I wouldn't make it, right? So I'm going to mention it kind of casually, and then I'm going to move on to what is actually the metaphor that I'm going to talk about today. So I have two graphs here. The one on the left is my friend network on Facebook from 2011, so a long time ago. And even a long time ago in Facebook world, right? Even at that time, the University of Illinois was the very largest component in my friend's graph. And of course, that has only grown over time. And it pretty much includes, I mean, at least in a, if not an actual sense, at least a symbolic sense, it includes all of you in this room. So that University of Illinois connection is kind of magical to me because it is both my, professional connection, my connections to you and to my colleagues. They're there. Well, it's also my social connection. It's a lot of stuff. It's like all the most meaningful connections have at their base this component of that graph. Now that's not entirely true because my husband completely eschews Facebook. And so, he's not there and he's glad of it. But is that true, dear? Yeah. All right. So I want you to just be aware of kind of that opportunity that being here affords you to have both your intellectual community and your social community all kind of tied up together in one big component. The other graph that I wanted to show you that connects people to one another is the one on the right. It was created by Jeffrey Herman and some other faculty at this department, and it reflects collaborative connectivity between faculty involved in the Academy for Excellence in Engineering Education. Okay? So this is a representative of an important subset of. So again, it's just a symbol for the amount of collaboration that takes place among faculty in service to your educational experience. Now, I think this is really cool because it means everything you learn, even if you're not CS. One of the colors there is CS. I don't know which one it is. Is Jeffrey here? No. One of the colors there is CS. Across the College of Engineering, faculty are working together very deliberately to improve your educational experience. Okay, so those are two things that I thought were sort of cool about the people connections on this campus. And again, I just want to reinforce that I think probably that graph of faculty, just a small subset of the kinds of collaborations that take place on this campus in service to your experience. But like I said, I can't talk about people. What I do feel pretty safe talking about for a minute are national parks. But I better get my notes. So I think it was Bree Chapman, Professor Chapman's daughter, who was a computer science graduate a year ago, who first pointed me to, she knew how much I love the national parks, and she first pointed me to an artist in residence program at one of the national parks. And here's how the artist in residence programs work. You go to the national park of your choice. I was going to choose Glacier. And you hang out for a month. And you talk to the other people that are there. The only problem is you have to do art. I got no skills. In fact, I think other than the desire to be in that place, I probably have absolutely nothing in common with that artist who's doing something fantastic there. But the idea was born, and I decided I wanted to pursue it, and so I started thinking about, okay, what kind of art could I do? And of course, the only kind of art that I have any prayer of approaching is algorithmic art, right? And so I made a list, I used as a premise the idea that you would start with a photograph of a beautiful place and you would transform it into something lovely, much like the application Prisma does on your phone, except that I would make it interactive and it would be sort of cool. People who came to the National Park Visitor Centers could upload their own pictures and play with them, and it would be really awesome. And so I started, grand visions, right? Yeah. So I started making a list of all the different kinds of art I would make. If you came to Pulse this year, I talked a little bit about the snowflakes that arose out of this obsession. This talk's different. It was a different art project. This one involved creating a stained glass effect on images. Okay, so yeah, that was what I was going to do. And I don't know when I found time, probably over a winter break, but I started out trying to figure out how I could transform images into stained glass. And furthermore, the cool thing about this, I think, was I used this opportunity to learn new software packages, right? Like this was my chance to freshen up my skills, to learn a new image library, an interactive image library for C++, and eventually this work would have improved CS225, or at least so I thought. So this was my first attempt. Okay, you're free to laugh at this if you want, but you can't laugh at the subject. So here's what I did. I took a picture and I sprinkled a whole bunch of random points, and I just mapped each pixel to the color of its nearest point in that sample set. Okay, so this is what's known as a Voronoi diagram among the points in the image. Okay, so you just map each pixel to its nearest center. I also want to point out that I didn't do this I didn't do this particular picture a couple years ago. I just did the idea a couple years ago. The picture itself is brand spanking new. So, internally we need to give a little celebration here for Quinn, the quintessential engineer, in her appearance on our campus. And hat tip to Sakshi, gosh. Yeah, this is a hard place right here, right now. Sakshi for getting this done, and Texas Instruments. But it doesn't look like stained glass. So I thought about stained glass, and I decided that at least in my experience, stained glass has sort of different size components. So my next attempt was this one. Okay, so if you've taken CS225, you know the genesis of this. What is that picture in the upper left-hand corner? That's the Quadtree MP, that's right. So I actually, believe it or not, yes, I can do the MPs. You guys were not supposed to laugh that loud. Nor that time. Recursive joke telling doesn't work very well. Okay, yeah, so this is the Quadtree MP. So what I did here is I took the centers of each of the regions and sped that collection of points through the Voronoi diagram clustering. It's kind of a clustering algorithm, not iterative though. And that is my office there. It doesn't look like stained glass at all. I know. You don't have to tell me. Okay, so what I did at that point was I'm like, okay, I got to talk to somebody about this because I clearly do not know what I'm doing. I went to find Jeff Erickson, and he wasn't there. So then I went to find... He would have told me no anyway. So then I went to find David Forsythe because he knows about images, right? And he told me two things, the first of which I'm going to discuss for a while. The second of which I'll say for later because I don't like it very much. The first thing he said was, oh, no, I'm not going to try to imitate David. No, I'm not. I'm going to resist. I would do it if he were here too. He said, what you need are super pixels. I went, ooh, that's got to be good. Okay, so let me make sure that I get my correct. Okay, so here's the purpose purpose of superpixels. As you well know, an image has lots of data associated with it. The idea for superpixels is that you can take an image and partition its pixels into disjoint sets. You're the only people who laugh at that. Into disjoint sets, each of which faithfully represents some patch of the image. And what that gets you is, instead of doing some kind of process or collecting statistics on every single pixel in an image, you can basically summarize the image in many fewer parts. Okay? So, luckily, the Scikit imaging library has great superpixel functionality, and I didn't even have to work this hard for that one. And I got that. So superpixels are often described as equal-sized, approximately, continuous, compact regions that honor important boundaries. Okay, so they do the right thing across color changes. Now, this is an extremely easy algorithm. All it does is it considers distance to be not only the difference between the locations of 2 points, but it adds in the cost of a color difference across that distance. Okay, so it's basically the Euclidean distance between 2 points plus some measure of the difference in color. So if you look, the color boundaries get a partition because those pixels, even though they're right next to each other, they're far from each other in the color space. Now, tuning this thing so that you have just the right weight of distance versus color is a matter of just playing with it in the context I was using it. I'm sure that people with real computer vision care about this a little bit more. So any question about that? I think it's kind of cool, right? One thing you might observe here is that I didn't pretend like each of my regions was a solid color of glass, because I just thought this picture was so beautiful as is that we would deploy that kind of stained glass where you're allowed to write on it a little bit afterward. Let's see. Oh, which brings me to my second conversation with David. One time I wasn't quite happy with this. I don't know why. I think I was bothered by the scaling issue between the color scale and the Euclidean distance scale, and I felt like you should be able to actually learn that, to know what the appropriate scale was in that distance metric, rather than just trying a bunch to see what you like. And David said, well, how will you know when you do a good job anyway? And I was like, well, I'm an artist. I'll know. It'll be beautiful. So that was where we left things. That was last week sometime. But the following connection occurred to me long before this. So it was last week when David said that thing, and it annoyed me to no end. But the following connection that I want to talk about, and this is a connection, I'm going to use it in the same sense that I use strongly connected components in the title. The connection is that I'm looking at this going, equal size continuous compact regions. Did you guys know there was an election last November? I'm the one who moved to Canada. Well, one of the issues that arose during the election and subsequent analysis has been the idea of representative elections at all, right? Like, does our democracy work as it is? And ex-President Obama has made this one of the things that he talks about regularly. He's called us to service in making sure that our democracy works. And the particular situation that came to mind when I saw this equal-sized continuous compact regions that respect important boundaries was the issue of, does anybody know? Yeah, exactly, gerrymandering, right? So all of a sudden, this thing that was completely frivolous in my mind has transformed itself to one of the issues of our time, in my mind, right? Because grandiose ideas, right? Okay, so let's talk about gerrymandering for a minute. I'm going to loop back around, I promise. So gerrymandering is I'm going to read this also to make sure I get it stated correctly. It's the redrawing of political boundaries to provide advantage to certain parties. And the idea is that if you drew boundaries just geographically, then you would not get boundaries that are shaped the way they actually are in our districts. Okay? Now, lest you think so. Lest you think that. Oh, and here is one mathematician's idea of what a better drawing of congressional districts might look like. And we'll talk about that in just a second, because I don't think when they did this, I actually don't think that they honored like important boundaries. I think they got the contiguous and compact part, which means kind of close to round, but I don't think they like had the jags that counties are going to make in congressional districts. But lest you think that this is a problem just down in the South, no. This is a similar comparison between congressional districts as they are now, and what would happen if you at least made them equal population and compact. Like I said, I don't know if they were honoring any particular metric on quality beyond that. As far as I can tell, the only districts that get this right are in Montana, Wyoming, North and South Dakota. Right? Even Nebraska, go Big Red, has some funkiness going on. All right, any question about that? So I want to take a little bit of a deeper dive, and I promise that I have a point to this. So how does gerrymandering happen? So consider population here, which is 60% blue and 40% red. I am affixing no particular political persuasion to this, okay? I don't intend any particular ideology associated with this. So this is just who lives here. And for the sake of the example, those people live in those spots, but you can imagine that similar arguments would hold sort of no matter how you draw these regions. Even if you mix things up, some of the same principles that we're about to investigate will happen. So these other three pictures are three different ways of dividing those 50 people up into 5 congressional districts. Okay? What I want you to decide for yourself is which one or two or three of those are fair. Which ones are fair? What does it mean to be fair? These are not questions that necessarily have answers. Okay? They are not questions that necessarily have answers. All right, I guess the only way to do this is to do the visual histogram. I want you to raise your hand if you think it is this first one that is most fair. Okay? And raise your hand if you think it is the second one that is most fair. And raise your hand if you think it is the third one that is most fair. Okay, so just so you're clear what was going on there, in this one, the minority has the majority of districts, okay? Just so you're clear that that's what's going on. Okay, all right, so the creator of this visualization went through and carefully counted. It probably took all of 30 seconds. And they pointed out that blue wins 3-2, blue wins 5-0, and red wins 3-2 in the last one. Now, if you want your districts to have the same representation as the people in the original population, then this one would be considered fair, like many of you said. Okay, but people do tend to live beside other people that are kind of like them, but that's certainly not ideal, and you certainly can't count on it. In fact, we would argue that we would try to move to the opposite. So, how does this go? The other observations based on this example is that the second one is compact, but in that one, blue has all of the seats, and presumably then all of the voice in any body. And then in the third one, it's neither compact nor fair, meaning if you actually designed a district that looked like some of those, you'd go, what the heck? It looks like a scorpion tail or something crazy, right? There is no meaning in no geographic meaning to that third one. Speculation is that's actually what's going on across our country. Okay, so we have this feeling of fairness. We have this feeling of compactness, but how will you know if you've done a good job? Oh, darn it, David. Turns out, though, in this context, there is an extremely recent answer. In this context, the answer is you look at whose votes are wasted. The observation is that if any group has more than half if the winning group has more than half the votes, then those additional votes are kind of wasted, right? You could have used them somewhere else. And moreover, for the losing group in a district, those votes were wasted because they tried, but they didn't. Believe me, living in Muhammad, I know how this feels. There are about 5 people in this room who get that. All right. Okay, so the idea of this metric of quality on districting is called minimizing the gap. I keep wanting to call it mind the gap, but it's minimizing the gap. What you do is you look at, for each party, how many of their votes are wasted, and you add them up and divide by the total number of votes, and that's a measure. The closer you are to 0, the less inequity, the fewer votes are wasted, the less inequity in the voting process. Now, I want to reinforce that this is a hot topic issue. This paper where the efficiency gap in voting was defined was published in 2014, and not in a tech or math journal, but in the Chicago Law Review. And it was done by, I believe, political scientists, and only in 2014. So the problem has been recognized for a long time, but the attempt to address it mathematically is fairly recent. And moreover, look, I don't write my talks at the last minute or anything, but yeah, okay. So just to reinforce, I wanted to point out exactly what that gap is. So if you look at our 3 examples, I have circled an example for each case of where the votes are wasted. So in this one, in the all red districts, 4 votes are wasted each, right? You see that? And in the all blue districts, wait, did I get that right? Oh yeah, 4 votes are wasted each. If you add all those up, you get a gap, or actually take the difference between them, you get a gap of 4 out of the 50 total votes. Now, there's some rounding issues there because our numbers are small, but the idea is the same there. The idea is correct. So the wasted votes here are all red. The blue guys are going, yes, we got them to waste all their votes. And there were no wasted blue votes. And then in this last one, the red votes, only a couple of the red votes were wasted. And I thought it was kind of interesting that you could actually take those little guy red votes that are, nothing's working, my pen's not working, nothing's working. The little red votes that are in the ones that are mostly blue, and swap them out, and the difference, or the efficiency gap doesn't change. So in that area of wasted votes, sometimes it doesn't matter where you put things, you get the same values. Okay, so all this did for me was to raise a gazillion questions. And here are some of them. The first one was Nate Silver. Nate Silver has a model for this. He's going to tell me exactly how to implement this in gerrymandering, and then I'll take that and I'll know. Another interesting question I had immediately was what happens in the limit? You know, like what are the bounds on what that gap can be given the distribution of people overall? And it actually makes me question the model a little bit to look into that. What could you do in a multi-party system? Is there a maximum likelihood estimator for this gap? That is, could you create an iterative algorithm which would be likely to converge, statistically likely to converge, based on this measurement of the gap? Kind of like the k-means algorithm. Is there such a thing that you could exploit here? And then, of course, this is the connection component. Can I apply this? Because after all, I really only care about stained glass. Can I apply this within a clustering algorithm on pixels? Well, I haven't done that yet. I want to understand some of this other stuff, some of these other questions before I try to apply it to my fun little project. But what I know to be true is that I started off frivolously on a project that I just thought was kind of cool and fun. And it led me into this world of notions of the meaning of democracy and equity. And then, after thinking about that for a while and getting a little frightened, but I got to, it was good. It took me back to the pixel realm with new information, with an idea, with an answer for David to be able to say, well, I know how I'll tell. I'll know my stained glass is great if there's a small gap. And he'll go, ooh, okay. All right, do you have any questions about this one? You have a question about this slide. What is the thing on the left? It's a tree. Always draw our trees upside down. The root is at the top. Actually, that tree was by Frank Lloyd Wright. He probably didn't want me to draw it upside down, but I did anyway. Okay. All right, so that's sort of the technical substance of the talk. I wanted to talk about implications of that. Of course, it probably doesn't surprise you that all of that heads straight to the idea and the notion and the conversation about diversity. But I want to break apart that conversation for just a second into inherent diversity, that is, the diversity that we are born into or with, like our gender, or our nation of origin, or our cultural heritage, as opposed to diversity that arises because of acquired characteristics, that is, the choices that we make, or the situations that we put ourselves into. So I know that you know that I care about the issues of inherent diversity in computing. And I care about it a lot. I talk about it any time I can for two reasons. One is that I think computing is really cool, and I want to be sure to remove all artificial barriers to anybody participating, because it's a blast, and it's lucrative, and it's fulfilling, and it keeps you young, sort of. I don't know. But the other thing is that I think any kind of diversity, inherent or acquired, serves innovation well, and we are all about innovation, right? That's what we're all after in computing. That's where we want to go, and we need lots of voices in order to make that happen. There's a lot of recent work that says diverse groups do better work, do more efficient work, they're more innovative, and the reasons for that are simply because people tend to listen more, people tend to take on the responsibility of speaking more clearly when they can't assume anything about people around them. So that's inherent diversity. Yes, let's just nod our heads and say we're all on board with that. What I want to spend the rest of the time talking about is, or not, I'm not going to force you. I want to spend the rest of the time talking about acquired diversity. the kind of diversity that comes from surprising connections between things you just kind of think are cool and things you know to be important. One of which is the example of algorithmic art and gerrymandering, but there are a gazillion of those. Gazillion examples of those. So what I want you to think about, and what I've enjoyed thinking about over the last few hours, well, yesterday's last few hours, were what are all of the opportunities that we create for acquired diversity of ideas? What do we do to cultivate, those opportunities for new ideas, for diverse ideas? So this is my illustration that I made that is purely an example of some of the things that I think are important. They happen to be important to me personally, but I think you could each draw your own illustration like this. So some things I want to expand on in this particular thing, things like travel makes you your space of ideas grow like crazy. The arts, concerts, eating good food, even if you don't think you'll like it. CJ, do you recognize this? Yeah, so CJ, I don't know if you know this or not, but that was what, a Thursday night dinner, I'll just whip that together after work, or something like that. She creates food like this. As far as I can tell, it's every night. So, sorry CJ, we're all coming over apparently. And I consider it to be magic, and I think she considers it to be a bit of a work of art and something that makes her world grow. Yes? Can I, yeah. Right, and her family benefits. And I benefit because I get to look at cool pictures and be inspired. What are other things? Be sure to read books. Protest if you feel like it. If something is important to you, like the national parks, protest about it. Learn about different cultures, listen to music, plant a garden. Julie, that one's not mine. I always wanted to plant the garden together. We didn't get to, but I do enjoy the flowers. So these are just a few examples. One thing I want to point at, well, I'll point it out on the next slide. Okay, now, so what does that inform? So that's, that's the other 8 hours of the day. For me, you have different things, and you probably at this point in your lives don't have 8 hours a day. But what does it inform? What does it do for you? Well, it shapes the way you navigate the part of your life that you have to do. That part that you're like walking in the shadows there, just kind of doing your work. You got to be thinking about something. You might as well let your space of ideas include things that you like. It includes tech. It includes the network of people that you put around yourself. By golly, it includes your experience here and the work you do here. You have an opportunity on this campus to take incredible courses. And I mean beyond Atmos 120. It's not the only one. Isaac, what are the other good courses?
I took coffee.
Yeah, the economics of coffee.
Yeah.
Okay, keep going.
Harry Potter.
Harry Potter, literature of Harry Potter.
Geology of national parks.
Geology, it's my kid. What else?
Arts and crafts.
Yeah, Nathan's in there too, yeah.
And will he graduate?
We'll talk about that in a second. CS 120, oh! Because his mama made him. As Bill is teaching me. Let's see, sports journalism, I got you. Yeah, okay. So, I don't know if all those courses have been great, but I'm pretty sure they're changing his worldview. You guys will have jobs, he might not, but there's gonna be a balance in there somewhere. There's going to be a balance. There has to be a balance. There has to be a balance, and I really wish that for you. Raise your hand if you've taken an ice skating class. I think it's pretty popular. Yeah, it's good, right? Greg, it's fun, right? Yeah. So there are opportunities that I don't know to think about for you. Only you can figure them out for yourself. Maybe there's a board game class. Maybe there's a board game design class. There's certainly a board game design class in town. All right, so that's that inspiration. I want to point out the kinds of things, the kinds of effects that a diverse view of ideas can give you. This is a list of the topics in which the grand challenges are separated, the world's grand challenges. So these are recognized to be the things we need to address on our planet. Poverty, security, education, food, environment, energy, water, good health. We're crazy if we don't think technology is going to be incredibly important to address all of those problems. And in order to have the biggest possible set of ideas to apply, you have to come to it thinking very broadly. All right, have I talked enough about this? You feel like, okay, all right, I'll take some courses. Okay, fine. But what time is the 2:41 final? Okay. Okay. I want to talk about this from another perspective as well. Same slide, different perspective. It's a diversity of ideas from a community view. Now you'll notice that the arts are here. This is Bella. Are you here, Bella? This is Bella and Kaitan. Is Kaitan here by chance? No. Is Sylvia here? Okay. So these are people that I know and love, and they do this. Or did. Sorry, Bella. I do know people that do this, right? And it is incredible to watch, partly because I can't do it. Not even close. Right? Oh, catch. Right? And I know that our world would be lesser, our idea space would be smaller if we didn't have people who did this. So even if we're not going to do the arts, humanities, or social sciences, even if that's not our calling, I think it's our burden to make sure that from a community perspective, the people around us have the resources that they need to continue doing them, because we benefit whether we like to recognize it or not, whether we take the time to recognize it or not. The people who work in those disciplines shape the breadth of our idea space. Okay. I think that might be it. Hold on. Oh, yes. So that's kind of the punchline for the talk. You support your national parks and the arts. I need to spend a couple minutes saying thank you. Thank you, Wade, for concocting this idea, and Corley for making this happen. This was really fun to think about the talk itself. And I can't even tell you the feeling of making eye contact with every last one of you. I'm so grateful that you are here. And not all of you are students. So thank you for being so bright and fun to teach, and fun to go to lunch with, and fun to talk about education with, and fun to dream with, and fun to, you know, dear. You know, there's lots of people, and fun to hassle Isaac. Nice. Okay, so thank you for being here. And thank you in advance for all the ways that you're going to address all of these things that the world needs you to do.
Okay. I think we have a couple things for you. So this is flowers. This is really loud. It matches your shirt. So this is a stack of cards from, I think, alumni, or a bunch of people. Current students, alumni, some people graduating, some people, yes.
you're not going to let me leave this room without crying, right?
I think we made the group chat make Cinda cry.
So I actually want to point out that the first voice I heard associated with the University of Illinois is in this room today, and that's Barb Ciccone. And this is, longer ago than either of us were living. What?
It's not fair to make me cry.
Oh, yes, it is.
It's okay, we're gonna make Cinda cry now. It'll be great. So Wade is pulling up a video of something that a bunch of us said to you or are saying to you right now. The video is also in the USB drive in that gift bag.
In this gap bag?
Yes. Where's Cinda? Are you crying? Yes. I did my job, that's all I needed to do. So we can all say thank you to Cinda. The department's having a reception in the atrium, so you guys are all welcome to join in. Thank you, Cinda, for everything, for shaping our community, and for bringing positive energy into our lovely CS lives.